and share and subscribe and like.
Friends, in this video we will prove an important process of finding a greatest common divisor. It is given by Euclidean, and therefore today now it is called as an Euclidean algorithm. It is based on a very important lemma which we will first prove. The statement of that lemma is, suppose GCD if A equal to Q into B plus R, uh, then GCD of A comma B equal to GCD of B comma R. Means these two numbers A and B and B and R have the same GCD. So let us prove this. Suppose that first, if D equal to GCD of A comma B, then we know that by definition of greatest common divisor, D is a divisor of A and D is a divisor of B. But then D is a divisor of A minus Q into B. Okay, so but what is meant by A minus QB? This implies that D is a divisor of R. So we have this D is a common divisor of common divisor of B and R. Okay, now if C is a divisor of B and C is a divisor of R, this is any divisor, divisor. Okay, but then it gives us C is a divisor of QB plus R. We have proved this lemma AX plus BY. So here we have taken this Q and R, coefficient of R is 1. So this implies that C is a divisor of A. Okay. Then what we get here? C is a divisor of A and C is a divisor of B. But C is a common divisor and D is a greatest common divisor of A and B. So this means that C is less than equal to D. Okay, so what we have? We have D is a greatest common D is a divisor of A, D is a divisor of B and D is a divisor of R. Whenever there is any number C which is divisor of B and divisor of R, then this C is less than equal to D. This implies that the D is equal to greatest common divisor of B and R. Condition is satisfied. D is the greatest common divisor of B and R. So we use this lemma to prove important Euclidean algorithm. Now if we have two numbers A and B, and we take that A is greater than equal to B is greater than equal to 0, then by division algorithm we know that A is equal to Q1B plus R1, where 0 is less than equal to R1 is less than B. Now if R1 is equal to 0, then uh, this B divides completely A and GCD of A comma B is equal to B if R1 is equal to 0. Now if R1 is not equal to 0, if R1 is not equal to 0, then we divide B by R1, divide this B by R1. If we divide this B by R1, we get another question Q2 into R1 plus remainder R2, 0 less than equal to R2 less than equal to R1. Again, if R2 is equal to 0, then obviously R1 is a divisor of B and GCD of B comma R1 is equal to R1. Okay, and if R1 is a GCD of B comma R1, obviously it is equal to GCD of A comma B. The process will stop. Again, the second possibility, if R1 is R2 is not equal to 0, then divide R1 by R2. If we divide R1 by R2, R1 is equal to, we get Q3 R2 plus R3, where 0 less than equal to R3 is less than R2. Okay. Now look at these values. We have this B is greater than R1, R1 is greater than R2, R2 is greater than R3. So the number is continuously decreasing, and somewhere we get 0. Okay, the process will terminate at some stage. Suppose that the process is terminate at R n. That means if we have Rn minus 2 is equal to Qn into Rn minus 1 plus Rn, where 0 less than Rn less than Rn minus 1, and Rn minus 1 is equal to Qn plus 1 into Rn. The process is terminated. Then the GCD of the two number Rn minus 1 and Rn is equal to Rn, and obviously it will be a GCD of A comma B. In short, if we write the uh, process, what we have done here, we have continuously the dividing by a remainder. Okay, so if we have this number A, and then we have divided A by B, we get one quotient and one remainder. Again we have divided B by quotient, we get another quotient R2 Q2, and we have divided by R1 and we get remainder R2. If R2 is not equal to 0, then divide R1 by R2 and we get Q3 R2 plus remainder R3. So continuing in this way, Rn minus 1 is equal to Qn Rn minus 1 plus Rn, and Rn minus 2 Rn minus 1 is equal to Qn plus 1 into Rn. So here 0 less than R1 less than B, 0 less than R2 less than R1, 0 less than R3 less than R2. Continuing this, 0 less than Rn less than Rn minus 1. So we have this process, and this is called as an Euclidean algorithm to find the greatest common divisor of A and B. And we know that how the greatest common divisor can be obtained, yet we have obtained by factorization of the numbers, prime factorization of the number. We have taken common factors and then we have multiplied that common factor and we have obtained the greatest common divisor. But Euclid have given us a different kind of algorithm to find a greatest common divisors. Okay, so to clear the idea, let us take an example of this Euclidean algorithm. And the process Euclidean algorithm is a very useful when the numbers are too large, since factorization of large number is not an easy process. It is quite lengthy process, but the by using a Euclidean algorithm it will become very easy. Suppose we want to find a greatest common divisor of 1 2 3 7 8 and 3050, like these two big numbers 12,378 and 3054. So when we go as a traditional method by factorizing it will be very lengthy process, but by using this Euclidean algorithm we can easily obtain the uh, greatest common divisor. So we divide this big number by this small number 1 2 3 12,007 378. When we divide, we get 4 into 3054 plus a reminder 162. Again, this is my b and this is a reminder. So we divide this 3054 by 162 and we get question as 18 and 162 plus reminder 138. Okay, again we divide this 162 by 138, we get quotient as a 1 and remainder as a 24. Okay, dividing 138 by 24, we have quotient is 24 and remainder is 18. Dividing this 24 by 18, 1 into 18 plus 6. Okay, and 18 is equal to 3 into 6 plus a remainder 0. So this shows that 6 is a greatest common divisor and therefore GCD of 12,378 comma 3054 is equal to 6. So you have seen that how we can find a greatest common divisor by using the uh, Euclidean algorithm, and again we can express these as this greatest common divisor in terms of ax plus by. It is quite easy. We write this 6 is equal to 24 plus 1 into 18 equal to 24 plus 1 into, we write this 18 as a 138 minus 5 into 24. Okay, so you can see that 24 plus and mm, minus 24, here is minus 24 minus minus. Okay, so this is minus minus plus, plus 5 and this 24, this is 6 into 24 minus 1 into 138. Again 24 is equal to 6 into 24 means 162 minus 138 equal to 6 into 162 minus 6 into 138 minus 1 into 138 equal to 6 into 162 minus 7 into 138 138. Okay, again substituting the value of 138, right here I am writing now, this is equal to 6 into 162 minus 7 into 138, 3054 minus 18 into 162 equal to 6 into 162 minus 7 into 3054 minus minus plus 18 minus minus plus 18 into 7, that is a 130 132. So we have 1 18 into 18 into 18 into 7, 8 8 into 7 56, carry 5 and this will be 126. So 126 into 162 plus 6, this is 132 into 162 minus 7 into 3054. Again substituting the value of this 162, 162 is equal to 12378 minus 4 into 3054 minus 7 into 3054. So this is equal to 132 into 12378 minus 4 into 132, 8, 3 into 4 12, carry 1, 4 ones are 4 and 1 5, 5 this is 5 minus 7, 5 into 3054 minus 7 into 3054 minus 3054 128 and this 7 135. Okay, so like this you can see that how we can write express this greatest common divisor in terms of ax plus by. So we have here 6 is equal to 132 into 12378 minus 535 into 3054, right? This is a 1378x plus 3054y. We have x equal to 132 and y is equal to minus 535. So this is an expression of greatest common divisor in terms of x and y. Here we have applied the Euclidean algorithm.
Hello guys, thank you for watching video.